So I'm glad to present our security analysis of the app model in business collaboration platforms. So these business collaboration platforms, such as Slack and Microsoft Teams, are productive tools designed for team collaboration with third-party integrations. However, as these platforms integrate more and more features, they have effectively transformed to a hub for sensitive resources. For example, we can have Zoom calls, file sharing, and even managing our cloud repositories, all from within the platform. And this phenomenon drives us to think, what if the apps are malicious? And if that is the case, can these platforms still enforce their security? And to answer these questions, we need first to understand how these apps work in practice. And in practice, these apps that we use are actually not hosted by these platforms, but by each app's own private cloud. Take Zoom, for example. The user needs first to interact with their BCP client to communicate with the BCP server, which then notify the cloud app about certain events, such as when the user posts a message to those apps. And after processing, the apps invoke API calls to react and finally respond to these events. But before using these features, we need to install the app into our workspace. Take Slack, for example. The app will first request permissions for installation, and this will include read permissions such as reading user identity or public messages, or write permissions like posting messages on, or sometimes on behalf of the user. And finally, the user approves these permissions. So up to now, we have assumed that all these apps are benign and that they will only do what they're supposed to do with these permissions. But we should notice that all these apps are actually web services hosted in the cloud, so we cannot guarantee that they are not malicious. And this forces us to look at these apps from a different threat model. That is a threat model with malicious apps. And actually, this threat model can happen in many different ways in the real world. For example, either the user is tricked by the attacker to install a malicious app, or if the user themselves is a curious insider of the workspace and install the app, or at some point, a previously installed app suddenly becomes malicious. However, analyzing security of these platforms and apps under this particular threat model is not that straightforward. And we have three main challenges. First, unlike Android systems, all these platforms did not specify their complete permission models. As a result, it's very hard for us to design a systematic security analysis. To overcome this challenge, we extract our own unified abstraction that best matches the communication for both Slack and Microsoft Teams. And after that, we find that all these apps are actually closed-sourced and unfortunately hosted on the cloud. So this prevents us from analyzing their source code or binaries. And to overcome this problem for each black box app, we examine all its possible interactions and find out those interactions that raise security concerns and implement our own apps to verify their vulnerability. And finally, because we cannot manually examine thousands of apps that are published, we have to estimate the number of potential attackers and victims based on their permissions. Now, following these three methodologies, we can finally conduct a systematic analysis of this app model in BCPs. And this leads to our first finding, that is a two-level unified permission model. At the first level, these platforms use cross-grain auth permission scopes to manage groups of resources. For example, here, the conversations in all private channels can be viewed as a group of resources, but we should notice that the token only declares a high-level permission, so at this level, the app will not be able to access any of the private channels. And to actually read those private conversations, we need to come to the second level, which we call the runtime policy checks. And this is fine-grained control of the instances within a resource group. For example, in this case, the platforms will implement some policies indicating that the previous token actually refers to a particular channel. And after that, the app can finally access the conversations in a private channel. However, when we analyze the execution of this two-level model, we find that both Slack and Microsoft Teams have violated some security principles. First, they violate the least privilege. While the previous two-level design looks good, in many cases, these platforms have implement ad hoc or even incomplete policies. For example, posting messages to channels is a high-level scope, and we found policies checking if the app was actually part of that channel. But for permissions like posting messages to users, We did not find any policy checks, so in this case, the app can either post messages to all entities or just do nothing. And second, it violates the complete mediation. That is, both platforms did not properly track provenance of resources. For example, in some use cases, the user might want apps to post messages using their identity, but the platform did not track if those messages were actually posted by a real user or a delegated app. So based on these two security principles, we continued our analysis and find that all three types of interactions among users and apps are actually vulnerable. And here I'll briefly introduce the high-level idea of each vulnerability and demonstrate one of the attacks with more details. First, for app-to-app interactions, we find a delegation attack. For example, a common use case is that the user wants some other app to post scheduled messages on their behalf, but the app can actually exploit this ability to talk to other apps as a user and access users' other third-party sources. And second, for user-to-app interaction, we find the command hijacking attack. And again, if we consider a use case where the user type a command to invoke some features of a third-party app, we find that another app can actually intentionally register a command of the same name and hijack this execution. That means the actual invoked function is not provided by the second malicious app. And finally, for app-to-user interaction, we find a case for privilege escalation. And in this case, if an app can read direct messages and post messages as a user, they can actually leverage these two permissions to also read all private channels, including other users. So how do we exploit these vulnerabilities in practice? Here we demonstrate a delegation attack that abused the integration in Microsoft Teams to merge malicious pull requests. First, we consider a scenario where the user integrates Bitbucket in Microsoft Teams to manage their code repositories. And with this integration, the user can actually send a pretty simple message to this app to merge their pull request. And in the meanwhile, the user also installed the Malicious and later app to schedule their messages. And to realize this feature, the app has to ask for legitimate permissions to write messages as a user. And we can see that at this point, this app is still benign and has not caused any fault. To deploy the attacker needs to first create a malicious pull request in the repository. And here, for demonstration purpose, we named the pull request as evil.txt. But in practice, as you may know, that there are some recent studies showing that many bumping version pull requests on GitHub are actually malicious. So we can simply name the pull request as bumping version. And once the malicious pull request is created, the attacker app can now interact with the Bitbucket app as a user. They can send the merge command twice to first initiate and then confirm the request. And at this time, because from the Bitbucket's view, it's the user but not the app who wants to send the request, so it will simply merge code as requested. And after that, the attacker can delete these messages to make the attack even more stealthy. And as we can see from the final page, the malicious pull request emerged and without any actual approval from the user. And we then conduct a prevalence analysis for each of these attacks. Because we cannot manually examine all these thousands of apps, we have to collect their permissions and count how many of them are capable apps with right permissions needed for the attack, and how many of them are susceptible apps with read permissions affected by the attack. As you can see, the first two attacks are potentially prevalent in both Microsoft Teams and Slack. They're about 10% to 30% of apps are capable of running the attack, and more than half the apps are potentially susceptible. And for the last attack, it requires a slightly rare combination of permissions, so we only found 11 apps. So how can these platforms mitigate these attacks? First, they should improve the design of their permission models. This will include fine-grained scopes where the delegation permission should be separated into apps and non-apps. And beyond that, the platforms should also design stricter runtime policies. For example, they should effectively check if a private message after sharing is still readable by a delegated app. And on the other hand, they should improve the execution of their permission model. For example, they should carefully track the provenance of the actions. And in this case, the other apps can decide if they should react to a user action or a delegated action. And finally, they should also provide explicit user confirmation to ask which app the user wants to invoke, especially when there are some ambiguation. Finally, we disclose all these attacks to Slack and Microsoft Teams, and they have confirmed these attacks, but regard them as social engineering, because from their point of view of these platforms, the workspace is a trusted environment, and the administrator will always correctly manage the apps. But we're afraid that this assumption can be too strong, so we provide some tips for administrators to ensure security. For example, they should consider limiting users from installing apps. And right now, by default, any user in the workspace can install any apps from any source. And second, they should also actively monitor the behavior of installed apps, because from our findings that the app can actually change their name and appearance to mimic another official app without notifying any party in the workspace. And finally, the administrator should only approve the delegation permission from trusted apps. Otherwise, it's very likely that those apps could be malicious and exploit this ability to abuse other apps. And this concludes my talk. Thank you for your attention. And you're also welcome to check out our paper and demonstrations for more details. Now I'll be open for questions.